Alright guys, so today we're going to cover Gay-Lussac's law, which is pressure versus temperature. So we've talked about Boyle's law, which is pressure versus volume. We've talked about Charles' law, which is volume versus temperature. Now we're going to talk about Gay-Lussac's law, which is pressure versus temperature. So the first question that we're going to work is, the pressure in our kitchen is just about 1 atmosphere. That's because we're close to sea level. The temperature we will assume is 298 Kelvin, which is about room temperature, about 25 Celsius or 72 degrees Fahrenheit. If I place a couple of chicken breasts in a pressure cooker, close the lid, and heat that pressure cooker to 100 degrees Celsius, which is the boiling point of water, what does the pressure inside rise to? So again, we just go through our 3-step process, pulling through, reading through the question and pulling out the information. So what are we given? The pressure in the kitchen is just about 1 atm. So we can take and underline this with purple and say that we are given P1, which is equal to 1 atm. Okay, let's read again. And the temperature we'll assume is 298. So we'll say T1 is 298. We can underline that in blue. T1 is equal to 298 Kelvin. Remember, the units are important. If I place a couple chicken breasts in the pressure cooker, close the lid and heat it to 100 degrees Celsius, so that's another temperature, we have T2 is equal to 100 Celsius. And again, we can look and see that we have 2 different temperature units here, so we have to adjust that. It's easy. We can just make this 373 Kelvin. Okay, those 2 things are equal. What does the pressure inside rise to? So we're looking for P2 in this case. So we are asked to find pressure 2. We have no idea what that is. Okay, so now we're going to do math. Not meth, right? So do math. We're going to utilize our equation. I'm going to use this one just because it's simpler to isolate the variable that I'm looking for. I'm looking for P2. So to get P2 by itself, all I have to do is divide both sides. My marker's getting a little dry here. Divide both sides by T1. So I have T1 on both sides. In that case, my T1 is going to cancel over there. Okay, so P1 times T2 divided by T1 is equal to my P2 value. Okay, so I can rewrite this simply as P2 is equal to P1 times T2 divided by T1. Then it's plug and play. Okay, so we're going to plug in our values, crunch the numbers, and see what we get. So P1 is 1 atm. So I'm going to start with 1 atm times T2. We're going to use the Kelvin because we always have to have our temperature in Kelvin when dealing with gas laws. Times 373. We're going to divide that by 298. So divide by 298 Kelvin. Then we can go through and cancel our units. I see that I have atm times Kelvin divided by Kelvin. Kelvin divided by Kelvin becomes 1. So that cancels out. So it is 373 divided by 298. And when we do that math, we end up with our P2 is equal to 1.25 atm. So if you've ever wondered how much pressure it takes to cook a couple of chicken breasts at 100 degrees Celsius, only a quarter of what you're used to in the atmosphere. Kind of interesting, right? Okay, so question number 2 for Gay-Lussac's law. We're going to see an aerosol can ruptures at just under 15 atm, 15 atmospheres. So if I take a spray can that is at room temperature, 298 Kelvin, and approximately 3.25 atmospheres, and I throw that into a campfire, I should be able to determine what the temperature of the campfire is, in this case in Kelvin, and we can convert if we wanted to. But So we see that we're given P1 is 3.25 ATM, P2 is the 15 ATM, and T1 is my 298 Kelvin. So it's asking for what is the temperature of the campfire. So that's my T2, okay? Because we started at 298 and we're going to heat it up to some value. So I isolate my T2 by dividing by P1. So divide both sides by P1. I end up with T2 is equal to P2 times T1 divided by P1. Then I can plug and play. So I plug in my values for P2. P2 is 15 ATM. Okay. T1 is 298 Kelvin. And my P1 is 3.25 ATM. Cancel out my atmospheric unit to leave me with a temperature unit. That tells me I'm doing the right thing because I was asked for a temperature. I'm going to get a temperature. Now I just do some basic math. 15 times 298. Take that answer, divide that by 3.25, and I should end up with 1375.38 Kelvin. Alright, so question number 3 for Gay-Lussac's law. We have here a plastic 2-liter bottle. We've stuffed a bunch of dry ice down in there. As the dry ice sublimates over time, the bottle will rupture. The initial pressure of the bottle is, we'll say, 100 psi. The bottle ruptures at around 150 psi. So the temperature at the time of the rupture was measured to be 18 degrees Celsius. What was the initial temperature? So you might have a question about, like, where am I getting all these values? I'm literally pulling them out of thin air, and here they are, right? So as we're working through this, we can see and identify where P1 is. This makes it a little bit easier because it says initial. So initial pressure, we automatically know that that's P1. P1 is starting pressure, initial pressure. Okay, so we know that that's 100 psi. The bottle ruptures at 150 psi. Well, if we're doing Gay-Lussac's law, we've only got 2 pressures to worry about. Initial pressure takes care of P1. That must mean that 150 psi is P2. The temperature at the time of the rupture, if the bottle ruptures at this psi and the temperature is measured here, that is automatically T2. That's what tells me that it's T2. So how do I convert Celsius to Kelvin? We add 273. So that's the conversion factor to move from degrees Celsius to Kelvin. So we take the 18, we add 273 to 18, and we end up with 291 Kelvin. So in this particular question, the question was, what was the initial temperature? So here again, we see initial temperature, so we can say that that is T1. So we're looking for T1. We isolate T1 by dividing out P2. Right? So as we divide out P2 both sides, we end up with T1 is equal to P1 times T2 divided by P2. We plug in our values, crunch our numbers, and we end up with 194 Kelvin. What is that in Celsius? All you'd have to do to convert that back is subtract that 273 that we added earlier. So we subtract out that 273 and we end up with negative 79 degrees Celsius, which happens to be the initial temperature of dry ice in its condensed form. Alright guys, so fourth and final question for Gay-Lussac's law. A car driving for 3 hours has created enough friction to increase the pressure of the tires to 1.9 times ATM. The temperature was measured to be 37 Celsius once we got out of the car after the drive. What would the pressure have been before the 3-hour journey if the temperature started at 25 Celsius? So again, we have to remember when we're converting Celsius to Kelvin, we add 273. So we got a couple of temperatures over here that we're going to add 273 to. All right, so we were given T1 is 25, and we started. That's another way we can identify a starting or initial or first temperature or pressure. So it started at 25 Celsius. So we take the 273 out of 25 to 298. That's where this 298 comes from. Okay, so pressure 2 is the other thing we were given because this was done after a 3-hour drive. So after the 3-hour drive, that tells me that it's pressure 2. And then temperature 2 came, we measured temperature 2 after the 3-hour drive, so that was 37 Celsius. Again, add the 273, that's where we get the 310 from. So we're looking for P1. What was our initial pressure? What was our starting pressure? So it increased the pressure of the tire. What would the pressure have been before? So that tells me that it's P1. Okay? So to isolate P1, we divide out T2. P1 times T2, right? Divide out T2 on both sides. So we end up with P1 is equal to P2 times T1 divided by T2. Plug in our values. P1 is 1.95 ATM. T1 is 290. I'm sorry, that was P2. T1 is 298 Kelvin. We divide that by our temperature or divide by temperature 2, excuse me. And we end up canceling out our Kelvin. When we do that math, we get the value of 1.87 ATM. So we started out at 1.87 times the atmospheric pressure. That's what helped keep the car up off the ground, right? No flat tires here. And then we drive for 3 hours, and that increases to 1.95. So we see that little bit of increase.